HPC systems are essential to better understand the world. Hi, my name is Izquierdo, and this presentation provides a brief overview of the project Formula Student CFD analysis that I have developed throughout the summer in the 84 Innovation Center in Ostrava. First of all, I will introduce some basic concepts related to the project, like Formula Student and CFD, and then I will go through the 5 main steps of the project. What is Formula Student? It is an engineering competition between universities all over the world that design and manufacture its own formula and then compete with each other in different countries. The competition is not only focused on having the fastest car, but also engineering decisions and methodologies are explained to the judges and provide around 1/3 of the total points. This project aims at helping at both ends, that is, making the car faster thanks to the simulation's results, and also improving the engineering rationale behind the design of the car of the Technical University of Ostrava team. What is CFD? CFD is computational fluid dynamics. Computational because the Navier-Stokes equations, that are the equations governing the motion of a fluid, do not have a closed solution and therefore many iterative computations are needed to solve them. And fluid dynamics because this goes about solving the motion of the fluid to later obtain the forces exerted by the fluid on a body, which belongs to the field of aerodynamics. CFD consists of 2 main steps: meshing, that revolves around dividing the fluid domain into small cells, as can be seen in the picture below, and solving, that consists of getting the values of the velocity, the pressure, and the rest of fluid and flow variables at each of the small cells. However, these problems are not easy to solve. As a rough estimation, if the mesh contains 100 million cells, if 100 iterations are needed to solve for the variables at each cell, being this a fairly conservative assumption, and if 1000 time steps are solved to have not a picture but a film of how the flow evolves, then that makes a total of around 10 billion operations to solve a single simulation run. Standard computers are not powerful enough to solve these problems within a reasonable time framework due to both their CPU and RAM limitations. What is the solution? Using more powerful systems consisting of more processors, that is, high-performance computing systems, HPC systems. Moving now on to the first step of the project, it involved the setup of the simulations. This requires starting and adapting all the numerical and physical parameters for the simulation to work well and be robust. However, this is just a small snapshot, and much more insight will be provided in the report to be published by the end of this project. Once the setup is completed, the next step is running the simulations in the supercomputer and benefiting from its computational power. This requires dividing the domain into smaller regions, and a processor will be in charge of solving each of the regions. The decomposition process can be performed with several different algorithms, being Scotch the best one for this complex case, and leading to a saving of 17.5% in time. The third step is to automate the whole process to make simulations faster and also easier to launch for the user. This was achieved via bash scripting, with 2 scripts for the 2 main tasks, in order to then upload 1 different job to the supercomputer with each script. But why 2 different jobs? Meshing and solution are very different tasks, based on different algorithms that essentially have different requirements. By splitting the simulation into 2 jobs, the user can define a different number of processors for each part of the simulation, and therefore get closer to the optimum number of processors for each of them, instead of being forced to look for a compromise. But how to know what the optimum number of processors is? Via scalability analysis, that defines how faster a program is when more processors are used to run it. The simulation in which this study is based is a 140 million mesh steady-state run for a FS car. For this case, the main graph shows that the meshing algorithm, red curve, scales worse and reaches a peak performance at around 700 processors, while the solver algorithm, orange curve, keeps on scaling decently even with more than 1500 processors. At a smaller number of cores, in the vicinity of what could be expected from a desktop computer, the total simulation time, adding up both contributions of this simple run, goes over 1 whole day. The graph at the right shows the smallest total simulation time achieved using a single job versus the 2 jobs approach finally adopted in this project. The gains are in the order of 12% in total computing time, and this difference would be even bigger for a larger number of cores, in the order of 3000. Finally, some images were obtained to better understand the aerodynamics of the car. In this first one, the pressure over the surface is shown, being the red zones the ones with the largest static pressure. Here the wake of the car can be seen from below it, the colors representing the value of the velocity. Now the wake is observed from a lateral view, where it can be checked how the rear wing diverts the flow. And this is a top view of it. And to finish with, streamlines starting at the front wing and showing the evolution of the flow over the car are shown in this last animation. Finally, I would like to thank Praise for setting up the Summer of HPC program, and the EG4 Innovation Center, the Ostrava Formula Student Team, and the Technical University of Ostrava for making this project possible. And of course my mentor Thomas for helping me out through the development of the project. Thanks for watching, and I hope you enjoyed it and learned something new.